Okay, now that you can see me. Okay, so math 329. Elementary Linear Algebra. So no matter what I said about the other version of the algebra that is presumably not elementary, they are not really that different. So the only difference is that the other linear algebra course, it requires proofs. And we'll cover very much a lot of the same material, just in a more applied sense, intended not for math majors. So that one meant for math majors, and this one for the rest of us. Okay, so as I said, what we're going to do is the review what amounts to pre-calculus, which is kind of silly to call it this way because there is no calculus in sight. So pre-something is what it is. College algebra, I suppose it would be a good way to put it. So remember courses like Math 127. Who took Math 127, 130? What kind of college algebra did you take?
I tested out of it.
Okay, yeah, that doesn't matter. But so the point is that some of the things are up here, there, and this is what we bring to the table. And what we're going to do is we're not going to overdo things about that is not related to the algebra, to the linear algebra, and we'll emphasize the linear algebra part of college algebra course. And then we gradually turn into things that are become more and more complex. The idea is actually pretty straightforward. It's pretty much aligning dimensions. So in college algebra, probably it is most of the time it's everything is one-dimensional, and then linear algebra goes to dimensions higher, 2, 3, 5, and 100. Okay, so let me quickly also ask you about the majors. So engineering, who is engineering majors? 1, 2 in the computer science.
Computer science.
Oh, everybody computer science. Who's left? So 2 engineering and the rest is computer science. Okay, that's great. So that's the angle that we're gonna take, and that is what's good, what linear algebra is good for, and we'll want for say computer science, and that's the managing data, because data is very frequently turned into a large big table. I mean, you take Excel, for example. What is it? If it's not a bunch of rows and columns, so those rows and columns form a table, and how it works for a table is a matrix. Okay, so that's the major thing that we're going to be studying. Okay, so but there are some concepts that we have to start early at the ground level of 0, and the dimension is 1. So let me try to. Well, there's one thing that is before we actually start talking about dimensions or anything like that. In linear algebra, it is just the concept of a function. Okay, so functions is the first topic. Especially if you have taken calculus 1. Who's taken anything beyond calculus 1? Okay, so
calculus 2.
2. Anybody 3? Did 3? Okay. Okay. So 4. Yeah. Which is okay. Well, differential equations. Yeah. Okay. So okay. Let me address that quickly. So calculus 1, function, and then tangent line. Okay, that's the big part of calculus 1, and this transition from the curve to the line is called either derivative or differentiation or whatever you care. But the point being is that this one, the end result is linear. Okay, so that's how linearity enters calculus. It is in fact the fundamental idea of calculus is making things linear, and they are, even though since their replacement is unfair. But if you zoom in on this point, then they're pretty much become indistinguishable. If you really zoom in, then the difference between these two curves becomes almost non-existent, like this. Okay, so that's the linearity of calculus 1, and that's as much calculus as we're going to mention. And then what happens later on, you cannot, in let's say 3, you don't have curves anymore, you have surfaces. Okay, so if you zoom in on a point on the surface, what are you going to get? What? What? Well,
Get a plane?
yes, you're going to get a plane. Yeah, yeah. So you zoom in. You can actually probably at some point you can experiment that. You just don't want to spend too much time. But any kind of computer graphics, if you zoom in, and it becomes flat. Okay, so that's the idea. So that's linearity, how appears in higher dimensions. Okay, so that's why you don't really have a lot of choices as to study or not to study linear algebra if you care about calculus, because you're going to have deal with high dimensional idea of linearity, and how do you progress from this is once again linear, and how do you progress from a line to a plane, and then, well, you have to ask yourself what's next. Okay, and even before you start to talking about what do I do in calculus of dimensions higher than 3, well, forget about calculus. What do you do? What's the next in this list of things? Line, plane. What's next? Well, so that's for us to discover in this class, and so that we could handle any dimension, not only dimension 1, 2, and 3, and so on, but also dimension n. So that's the linearity, and you either use whatever you've learned in calculus 3, which apparently we have only one person, to make your life in this course easier, or vice versa. If after this course your calculus 3 shouldn't be as much of a challenge, because you will learn to think multidimensional, and you will just recognize linear algebra everywhere you look at in calculus 3. Okay, so but there is even bigger picture here, and that is functions in general. They're not necessarily functions of numbers, which is what you saw in calculus 1, nor it is multidimensional things as you see in calculus 3, but also functions as in the most abstract sense of the word, and that is simply as assignments of numbers of one set of quantities and another set of quantities, or objects of alien nature, and there is a correspondence between them. So you may have seen this, but not in calculus, because in calculus you will become very specific, like here, and you talk about numbers. So functions are input number, output number. Okay, now, well, that certainly is a very narrow view of functions. Even in calculus, very soon will have to step outside of that. But in general, and wherever you are, whatever you're doing, and certainly computer science in particular, is this is what we are. That's what we understand by a function. So once again, a set of whatever and a set of whatever. So one is called the domain. The other one is called, well, there is no really a good name for it, but okay, I guess I avoided using the word. The range is, as you can see, is not really descriptive, because it excludes the points that are not being hit by this function. So this is the range. But there are more points. There are more possibilities there. It is, and I was thinking about it. It's just, I hesitate to use such a fancy word that is really well, just as well, since you brought it up. So it's on you now. Codomain. Okay, codomain as the kind of a dual things of the domain. Okay, so there they are related to each other in a kind of an indirect way. So you could remember that you can reverse them, but not always. And they might have really nothing to do with each other. Okay, so once again, I don't want to define what the function is, but we think of them as simply correspondences between two sets of objects, and the only requirement is that there is only one output for each input. That's all. Go with me. Actually, that's the second part. The first part is there is an output for each input. So it exists and is unique. That's another way to put it, as in mathematics we like to put it. And so like I said, in terms of these silly arrows, they are really very descriptive. Every point on left, every object on left has to have an arrow starting from it, and there's only one arrow. So that you cannot have two arrows like this. So that's the second rule. And the first rule, you cannot have an object in the domain without an arrow. Okay, so these are the requirements. That actually already takes you a little bit away from the traditional view that you on functions that you see in calculus and before, and that is they're talking about the functions of, say, real numbers, and then you look for the domain through examination of the formula of the function. We're really not talking about that anymore. We assume that the domain is supplied with the function. And indeed, we're not going to be worrying about division by zero. There won't be any division. Okay, there won't be any square roots of, well, there might be at the end some square roots at the closer to the end of the course. But other than that, the domains is not a concern. So the operations that we stick with in linear algebra are addition and subtraction and multiplication. And there is no division, there is no logarithm, there is no trig functions, and so on. And so that's why, not that's why, but and the view on functions is in fact more advanced, and that is once again the function it is an abbreviation for correspondence. Well, in chronological order, it is domain, codomain, and the correspondence. Between them. Well, not between them, but from 1 to 2. From the former to the latter. Okay, so exemplified by this, or illustrated with this little pictures, once again emphasizing that there might be missing targets. Okay, so when there are insert space, insert space. Nope. Okay. That's awkward. Okay, so then the question that I want to ask you is, what if there are no missing targets? It is an informal word, but I hope you see the picture and know what I'm talking about. So once again, there might be missing ones. What if there are no missing? What do we call such a function? No. onto. And 1 to 1 is 1 to 1. Okay, so what's the question? The answer, I will provide the answer for the, what's the question? Yeah, what's the question? The answer is 1 to 1. So what's the question? So every well, let me just use there's only one arrow arriving to each target.
Okay.
So what if there is, so this is only one, okay, one arrow for each target. So then it's called 1 to 1. So onto means that we do not miss any. So if we have whatever points we have here, we hit every one of them, maybe multiple times, by the way. It is when it is not multiple times, but only once, then we are talking about 1 to 1. They could still miss some of them, but with those that are being hit, they're hit only once. Okay, so these are issues are important, and they are important in calculus, but especially important and simple to handle in the linear situation. So let me just illustrate this. So these questions now for linear functions. For linear functions, so we have, well, let's say, so f. Well, there's once again another more advanced way of beyond calculus of we're looking at things in mathematics is what's linear, what's not linear, and f of x is equal to mx plus b is linear, but it's not really the case anymore. Okay, so linear functions do not have that plus b. So that's what we have been taught in pre-calculus and calculus, that if it is still language that is being used, there's a mismatch of language, like in linear algebra, that plus b makes functions non-linear. It's not linear anymore. Mx, period. That is a linear function. Okay? So 3x is linear. 3x plus 1, not linear. So we will get into why this is the case, and that why this extra coefficient kind of ruins everything. And on the other hand, it's really no big deal. You can always edit it whenever you want. And so you just have to be aware of the difference in the terminology. Okay, so for linear functions, let's take for these very simple functions. Look at it. There's how many are there linear functions so far? If we're talking about real numbers. There are as many as numbers. So what is it? It's simply a multiplication by a number. By m. So that's the linearity is really some kind of a multiplication by a number. Okay? So that is actually also another idea about functions. It's look at it right here. I have a formula on one hand. In the circle, in the word circle on one hand. On the other hand, I have a description of f in the box right there in purple. They're equally valid. So we describe functions with formulas if we can or we want to, but we also can describe them with nothing but words, and that works out very, very, very fine. So as you can see, there is no ambiguity in that description over there. We multiply the number by m. That's it. So that's the correspondence. That's the rule of computing one from the other. You can think of it in terms of computing. So x. So again, I can. Okay. So x input plug it into this box, and what does this box do? Multiply by 3, and then y output. Okay, so as you can see, there is really no formula to talk about, but that is a valid way to describe functions. And it's a very nice diagrammatic way to represent things, because if you have 1, you can have 2. So what can you do with it? What if I have another one? Multiply by -2. I could wire them together like this. So I multiply by 3 first, and then multiply -2 in the next step. And the name for this is, in mathematical terms, not in terms of computing. What do we call this? 2 consecutive computations, 2 consecutive functions applied. No.
The procedure?
No. Well, what's the formula? So x, then it is 3x, and then it is -2 times 3x. What is that? Does this, the parentheses, doesn't remind you of anything?
Order of operations.
It is, but the word that I'm looking for is composition. So that's what an algebra is called when you combine functions consecutively rather than in any other way, right? So you can combine, you can add these two functions if you want to. That would be like a parallel computation. But in order to carry out consecutive computations, if you need a composition, so you certainly can think of a lot of things done the way it's done in computing when numbers are processed in a consecutive manner. So the input of the first function, the output of the first function becomes the input of the second, and you can go on, and the word is chain, and that's where the chain rule comes from in calculus 1. Not that we're going to do any differentiation, but certainly it matters, so that the chain could be as long as you like, and it's simply composition of functions. Okay, so I got distracted a little bit. So that's how, because that's an important way to describe functions. But now we understand what linear functions are. How do we? Let's try to classify them in terms of them being one-to-one and onto. It is very simple. So okay, so classify linear functions in terms of, well, how about one-to-one first? It just doesn't work. Finally. Okay, so what can you say about it? Linear functions. So once again, it's simply f of x equal mx. So we have right here in front of us all linear functions in dimension 1 listed. So for each real number m, there will be a linear function y equal mx, right? So one for each real number m. Okay, so then you can guess that some of them will be one-to-one and some will not. Okay, so I don't want to go all the way back and try to figure out what it means in general. Let's just look at linear functions. And so one-to-one and onto. So one-to-one. Well, let me just draw all the possible linear. Oops. linear function. So remember the y-intercept is 0. So only, sorry about that. So the graphs will all be passing through the origin. So these are linear functions. And by the way, what is the meaning of M? Yeah, I mean, can you see it on the graph? Yes, M is the slope. Okay, so I have a bunch of them, and they kind of give you the specter. Almost almost all the straight lines through the origin are here, with the exception of what? One straight line we have to omit.
The
vertical line, because it's not a function. Okay, but otherwise all straight lines are here, including the horizontal one, right? Okay, so which ones are one-to-one and which are not?
They're all one-to-one except for the horizontal one.
That's right. They all one-to-one. Except, well, pretty much f of x is equal to 0. So m is equal to 0. So all m is not equal to 0. You have one-to-one, and if it is, then it's not. Okay, so that's, as you can see, it's very simple. You might remember that might, if one function were not linear, we would be doing a lot more trying to figure it out. So think about polynomials, for example. Can you tell what polynomial is one-to-one, which one isn't? We know that quadratic polynomial is not one-to-one. That's all. Okay, so and the second question is the same about Onetoone. So here, the question number one, that every output, so let's make it clear, these are the inputs. And in this manner, they give me the outputs. And once again, if there is any slope, there will be only one input for each output, right? Because I can always retrace my steps. So I pick a point here, okay, and I can always retrace my step and find and get back to find x. For each y, I can find x. That's one-to-one, but it's also I got confused. So for I can retrace my step with no ambiguity. So there is only one input for each output, right? So that's what I did over here, right? So if I start with y, I can find x, as long as it's not horizontal. Because if it's horizontal, then there will be each input gives you 0, so that doesn't give, so that's not one-to-one. Okay, now what about Onetoone? So once again, look at the picture and ask yourself which ones are Onetoone. So the question is, are there any y's that haven't been hit in this manner? So is there the holes in the domain? Yeah? Okay, so what's the answer? Except for, yes. So all Onetoone, so m not equal to 0, except f of x equals 0. M equals. Okay, so as you can see, classification is in that manner a serious issue for functions. In general, for linear functions, very specific, but it remains this way only in dimension 1. So that's fine. It is okay. We're doing dimension 1 right now. So all the concepts that we are looking at right now, they will come up again and again and again once we are going into high dimension. So this is dimension 1. The input one-dimensional, output is one-dimensional. They could, both of them can vary and pretty much be arbitrary. And then the question about one-to-one Onetoone will reappear. Okay, and as you can see, there is one exceptional linear function, f of x equals 0, that is neither one-to-one nor onto, and the rest of them are very good. They well behaved in that sense. Okay. Okay, so one-to-one onto. We discussed those basics from pre-calculus. Functions being one-to-one onto, and then the compositions. Okay, so these are three very concepts that really you go into calculus and they don't come up a lot, unfortunately. But here they are very very central. So another thing that we need to care about in dimension 1 still. So functions are good, but there's one thing that we shouldn't overlook, and that is the actual functions come, at least in calculus, they come after relations. So you remember what relations are? So functions are like, like machines processing x's into y's. And relations are, so thereby we establish a relation between x and y. That's what function is, but there are more general relations that are not functions. So remember any? It's, well, sometimes they're called implicit functions. Well, this is one. So as you can see, y is not expressed explicitly in terms of x, but there is a relation between them because, in fact, you could actually get a function from it if you want to do algebra appropriately. Just solve it. Solve for y, and you have y equal minus x plus 1. Okay, so you have a function. Okay, so okay, and as you can see, it is more general. So for every relation, we'll give you a function, but not necessarily. No, every function gives you a relation, but not necessarily vice versa. And do you remember examples or one example of a function that does not, a relation that is not a function? A relation. So in other words, you look at it, it's really not. This pretty much captures the whole story, except that this one is linear, so it's especially simple. But you might remember this. Once again, stepping outside of linearity and linear algebra. What is this? It's a circle, and so is it a function? Not a function because you cannot express x in terms of y in terms of x uniquely. Okay, nor vice versa. Okay, so this is y and this is x. As you can see, you might remember the vertical line test as well as the horizontal line test, because it is possible that if we are trying to capture the explicit relation between x and y, we could go with one or the other, x in terms of y, y in terms of x, and it would be equally good. So we have to actually watch for both of those properties. But once again, if we concentrate on functions that are linear, as one in the left-hand side, then we are in a better place. So let's get straight to the point, in that you may have seen it. A general, there is no word for it. This, or I just don't remember. General equation of a line on the plane. Remember that one? So y column x plus b, it is an equation of a line, but it is missing a vertical line. Okay, so all vertical lines are missing. So to take care of those, we write them implicitly. Remember? Ax plus by is equal to c. Here a, b, c are real. And we have to have an extra restriction, not both a and b are 0. So if both of them are 0, then we're not getting a line. But if one of them is definitely not 0, then we have a line. And some of them could be vertical. If one of them is equal to 0, then you have either a line, either vertical or horizontal. Okay, so yeah. A is equal to 0, you have by is equal to c, or y is equal to, a is equal to 0, b is not equal to 0. Then you have y equals c over b. That's a horizontal line. And so that's case, it is an extreme case of when 1 is equal to 0, and then the second extreme case is the opposite. A is not equal to 0, b is equal to 0. Then you have instead ax is equal to c, or x is equal to c over a, and this is a vertical line. And then the rest of the line with slopes will also be present. Okay, so as you can see, I tried to not to speak of functions here because that's a kind of a slightly separate issue that we are facing here. There are no functions here, but we do want to represent all straight lines on the plane at once. And as you can see, it takes 3 numbers, but not in a unique way. So x plus y is equal to, say, 1. How about 2x plus 2y is equal to 2? What's the relation? Both of them are lines. What's the relation between the lines? Okay, so what does it tell you?
Are they parallel?
It is the same line. It's just the same line. So, so a relation, like you said, if you take 1 and multiply by 2, and then you get the other, but it means that the relation between x and y doesn't change. You multiply by 2, the relation does not change. It's the same pretty much equation. Remember solving equations, and you do operations like that to the equation, and it gives you an equivalent equation. What does it mean? Solve an equation for x. We know what does it mean to solve equation for x and y. It means that finding all points x and y satisfying the equation. Okay, so we'll talk about that next time.